Welcome to the video on elimination. So you can see I have a little helper in the background. During the week when we talked about substitution, we looked at an alkyl halide that had a good leaving group and we reacted it with a nucleophile. And that nucleophile replaced the leaving group, and we got our substitution product, and our leaving group was free. We literally substituted the OH in place of the bromine, and so they just switched. In the next section, we're going to be talking about elimination. And elimination is different. What happens with elimination is we start with a similar or the same alkyl halide, and now instead of adding a nucleophile, we add a base. Now, we'll get into it, but nucleophiles and bases are very similar. But we'll find that some reagents definitely work better as bases, and other reagents definitely work better as nucleophiles. A lot of that depends on the size and the strength of the electron density. Right now, we're just going to say it's a base. Let's draw this a little different. What happens in elimination, if we draw out those hydrogens, is that a base removes a proton on the beta carbon to where the leaving group is. So here's where the leaving group is, and then the beta carbon, the one right next to it, a base removes that proton, and then we end up with a double bond. So we eliminate the leaving group and a hydrogen on the atom next to it. And so this is what our product looks like, plus our protonated base. So in substitution, we had SN2 and we had SN1. If you recall, SN2 was substitution nucleophilic bimolecular. That was a single step where we had the nucleophile and the alkyl halide come together in one rate limiting, the only step to form our product. In substitution nucleophilic unimolecular, we needed to have the leaving group leave and then the nucleophile attached. And so that was a multi-step reaction, right? And we remember all the details about each of those different things. So for elimination, we have the same thing. We have elimination bimolecular, or E2, which means that we have a single step where the base pulls off the proton at the same time that the leaving group leaves. So we're going to have a nice transition state to draw there. And we also have E1. An elimination unimolecular is where we have our leaving group leave, and then in a second step, we have the base pull off the proton to get our elimination product. And so let's take some time in this video going through the difference between E2 and E1. And to be honest with you, E2 is very similar to SN2, and E1 is very similar to SN1. A lot of what I'm going to say is almost review because we know it with SN1 and SN2. And so I'm going to cover both of these in one video. Let's start with E2. So if we look at an example of E2, we might have this reaction where we have this alkyl halide, and we're going to react it with this base. So you'll see that OH can also be a nucleophile. So there's going to be some overlap here, but let's move forward. So this is the alpha carbon and this is the beta carbon. And so we have one of the lone pairs on our oxygen reach out and remove the proton that's on the beta carbon. The two electrons that are in this carbon hydrogen bond hop over and form a double bond in between the alpha and beta carbon, and the leaving group leaves. And so our products here are this alkene plus water plus the leaving group, the halogen. Just so you know, this is also called dehydrohalogenation. It's just another word for this reaction. We're taking a hydrogen and a halogen off, and we get this alkene product. This is a bimolecular reaction, so both my base and my substrate are involved in the rate limiting, or the only step. And so if I were to write the rate expression of this reaction, it would be some rate constant times the concentration of the substrate times the concentration of the base. And if we drew an energy diagram for this reaction, it's going to be a single step. And we have to think about a transition state. So here's our starting materials, and here's our products. And so if we draw that transition state, we have our brackets, and we have our original alkyl halide. I'll go ahead and put that back in green. So we have our original alkyl halide. And in red, I'm going to put the bonds that are being affected in this reaction. Okay, so there's our original alkyl halide. And so now if we bring our base in, there's our OH, and the OH is going to start to form this bond, right, to take that into water. And then this bond is going to start to break. And then the double bond here is going to start to form. And then the bromine is going to start to leave. So that all happens in a single step. I will highlight where all the partial bonds are. Here's a partial bond, here's a partial bond, here's a partial bond, and here's a partial bond. And that's in the transition state. So just as in substitution, our leaving group needs to be a weak base. Please note that I wrote nucleophile here, but I meant leaving group. So the leaving group has to be a weak base. The nucleophile doesn't even exist in the E1 and E2 reactions. To recap, the leaving group needs to be a weak base. It has to be weaker than the base that's pulling off the proton. So we need a weak base. And so again, iodine is going to be a very good leaving group, bromine also, then chlorine, and then fluorine. So iodine is one of the best leaving groups. Fluorine is less reactive. Iodine is very reactive. OH minus will not leave. We'll learn later that in order to remove an OH, we have to trick it into leaving. So we have to protonate it, whatever we need to do to get that OH to leave, but the OH will not leave. Now I want to introduce the fact that we actually have a couple different hydrogens that could have been pulled off. For example, I don't know if you noticed, but up here in our starting material, we also have this beta carbon with this hydrogen. And so with elimination, very often we're going to get a mixture of alkenes, but the bottom line is we're going to want to form the most stable alkene. So if we did in fact pull this proton off instead, have this double bond formed, and then have leaving group leave, that alkene would look like this. And some of that is formed, but this is our major product. And the reason that's the major product is because we're going to form the most stable alkene when we can. So the stability of alkenes, we have tetrasubstituted is the most stable, and then we have tri-substituted, and then we have di-substituted, which can either be this way, these are about equal, this way. So this would be the trans, and then the cis is less stable. And then the least stable is a single substituent. And then, of course, no substituents would be the very least. And so that's the order of stability of alkenes. So whenever possible, we are going to form the one with the more substituents. So we're going to basically get deep into that molecule and pull the proton off that will give us the most substituted alkene. So a small base is going to easily be able to get in there and pull off the one that's kind of inside. Now I'd like to introduce you to the Zaitsev rule. The Zaitsev rule says that the more substituted alkene product is obtained when a proton is removed from the beta carbon that is bonded to the fewest hydrogens. We come up here and use the highlighter. This carbon has less hydrogens, therefore this hydrogen is going to be pulled off. This carbon, however, has two hydrogens on it, and so this one right here is not going to be the one that gets pulled off for the Zaitsev product. Let me repeat that. The more substituted alkene product here is obtained when the proton here is removed from the carbon that is bonded to the least number of hydrogens. So now let's talk about the substrate. What kind of substrate do we need for E2 to happen? So this is one where it differs from SN1 and SN2. E2 prefers to have a tertiary alkyl halide, and then secondary, and then primary. So more substituents is better, and that's because of Zaitsev's rule. So E2 prefers to have more alkyl substituents on our final double bond, so we want a more substituted starting material. Now I want to talk about the base. So we need a strong base. So for E2, just like for SN2, the base is part of what gets the whole thing going. So we need a nice, strong, charged base. But we can have different size bases. For example, if I have terp butoxide instead of just the hydroxide, so that's going to look like this, where we have a big, bulky base. Got a great negative charge on that, but it's this big, huge, bulky base. This base is so big that it's not going to fit into the molecule and pull off like a hidden hydrogen. This big base is going to actually pull off that hydrogen that's accessible, So it's going to pull off the hydrogen that is going to ultimately give us the non-ZSEV product. It's going to pull off the proton that's available, that's easy to get to, because this big bulky base can't fit into a molecule and pull off this hidden hydrogen. So it turns out that there's a name for the other kind of alkene that's formed, this one right here, where we use a big bulky base. And that is called the Hofmann product. And so the Hofmann product is when we form the least stable alkene. So big bulky bases affect the product distribution, resulting in the Hofmann product at a higher percentage. And tert butoxide is the one that is most common. And so with this base here, we're going to form the Hofmann product. And with this little base up here, the OH minus or methoxide CH3O minus, those are small enough that they're going to give us our ZSEV product as the major product. So we have Hofmann product, and then we have ZSEV product. So in the PowerPoints that I've posted, you can see a bunch of other big bases and how they distribute between ZSEV and Hofmann product. So if I quickly recap E2, the rate expression is such that we have a bimolecular reaction. So the rate depends on both the base and the substrate. Our energy diagram is one step, so we have to worry about the transition state. The transition state includes the base and the alkyl halide, and we have this collection of bonds that are broken and formed. The base needs to be a strong charged base for E2. The leaving group has to be a weaker base than the base that's pulling off the proton. And just like in SN2, we need to have a nice weak base that's going to be stable on its own, because it does stay on its own here. The substrate in E2 needs to be tertiary, then secondary, then primary. Again, if we can form conjugation where we have double bonds already in the ring, double single, double single, double single is a stabilizing force. So conjugation also helps in our substrate. The product that's formed, depending on our base, the product that's formed typically is going to be our most stable alkene because of ZSEV's rule. If, however, we have a big bulky base that can't get deep into the molecule, we're going to form the Hofmann product, in which case our product is the less stable alkene. Here is the list of stabilities of alkenes, so you have that. There is one more thing that I have to talk about for E2, and that is the idea of antiperiplanar. Antiperiplanar is the required conformation of our substrate in order for E2 to happen. So the base has to attack from the opposite side that the leaving group leaves. So for antiperiplanar, if we look at our starting material here, the hydrogen up here and the bromine down here, these two groups right here need to be anti to each other, meaning they have to be on the opposite side of the molecule and they have to be in the same plane. So if we quickly draw dash wedge here so that we can see what I'm talking about here. So if we have this molecule, the hydrogen and the bromine are both in the plane of the screen here, and they're opposite each other. So in order for E2 to happen, this is the positioning that has to be. Our strong base is going to pull off this proton on the opposite side of the molecule for where our leaving group, which is also negatively charged, right? We're developing a negative charge as it's leaving. So those two things have to happen on the opposite side of the molecule. And so we are going to have what is called an antiperiplanar conformation in order for E2 to happen. Antiperiplanar. Another way to describe that would be that if I had my base coming in from this side to pull off a proton, this would get in the way. That is E2. Now, if we move on to E1, E1 is actually much easier. So for E1, what we have is we can use the same substrate that we used for the E2. Let's start to talk about the base. The base does not matter that much. It can be neutral, and we'll see why. The leaving group, however, has to be great. And that is, of course, because just like in SN1, the leaving group leaving is the thing that gets the whole reaction starting. Let's see what that mechanism looks like. So in the first step of E1, the leaving group leaves, and we form this carbocation intermediate. And then in the second step, our base pulls off the proton and then forms the double bond. For some reason, my eye pencil did not capture this in real time, so I fast forwarded in terms of the display, but please try to follow along with my speaking. Now, in terms of the base pulling off the proton, it can pull off that top proton, or it pulls off the proton and forms the double bond. And so in E1, we get a mixture of products. Our nucleophile can pull off either proton, and so our products for this reaction are going to be the same products that our E2 gave us. And Zaitsev's rule absolutely follows. So the more stable alkene is going to be formed at a higher rate. And so that'll be our major product, is the one that's more stable, just like on the previous slide. But we do get some of this product as well. So with E1, we're almost always going to get a mixture of products. And if we looked at the rate expression for this reaction, we have the rate equals some rate constant times the concentration of the substrate. This is elimination unimolecular. Only the substrate is involved in the rate limiting step. So if I draw the energy diagram, we have carbocation intermediate, and then we have our product. So in this situation, having a neutral nucleophile does not add an extra step because our product ends up also being H3O plus. That's charged, and that's okay. So here's our starting material, here's our carbocation, and here is our product, which is an alkene. So just like in SN1, E1 has a carbocation intermediate. So you may be asking, how can such a weak base pull a proton off of a carbon that is sp3 hybridized? When we learned about acids and bases, we said these are not acidic protons at all. And so it turns out this positive charge is what really changes the pKa of this guy right here, making this absolutely possible. In terms of the leaving group, we have to think about two things. We have to think about our alkyl halide and the stability of the carbocation, and we have to think about the weak basicity of the leaving group. So both of those two things come into play in terms of leaving group. So leaving group, just like in all of them, we need a weak base. And then in terms of what alkyl halide we need to start, anytime you can have, right, we have to make a carbocation that is stable. If I draw carbocation stability, I put it in order. So if we have benzene, which I'll abbreviate that way, with a tertiary, that's going to be about the same as an allylic that's tertiary. So those two are about the same, which they're more stable than a secondary benzoic. So that's the benzene here with a secondary, which is about the same as a secondary allylic right there, about the same as a tertiary carbocation, which looks like that. And then that is more stable than a primary benzoic, which looks like this, which is about the same as a primary allylic, which looks like that. And then it's about the same actually as a secondary. And then, of course, that's better than a primary. And the least stable one is actually this one, where we have a positive charge on the double bond. So that is very unstable. So this gives you an idea of the order of reactivity of substrates coming in for an E1. Remember, we need to have this positive charge stabilized. And so if your substrate can look like anything up at this end, then that's going to be improved reaction rate. And then I have to mention that anytime you have a carbocation formation, we have to be thinking about rearrangement. So rearrangement is when we have a carbocation that if we either have a hydride shift where a hydrogen and its electrons switch places with the carbocation, or a methyl shift where we have a carbon and its electrons switch places with the carbocation. Those things are going to happen. So it's one of the things about E1 and SN1 that is challenging, and we have to try to figure out how to make that all happen. So for E1, a quick recap. It is unimolecular, so our rate expression only has the substrate in it. It is 2 steps with a carbocation intermediate. The strength of our base does not matter. It can be neutral, so it can be a weak base, because once you form that carbocation, it changes the acidity of the proton. So our base can be neutral, and most often is. Our leaving group has to be great, right? This is the first step, so our leaving group has to be great. Our carbocation has to be stable, and we have to be careful about rearrangement. So here's the order of stability of carbocations completely. We're going to get a mixture of products. The most stable alkene is going to be favored over the less substituted alkene, because eliminations can actually be endothermic, which means that the product is actually potentially higher in energy than the starting material. So if that's the case, then we often can add heat to reaction that will allow the elimination to take place. So we can add in the arrow of our reaction, we can add the word heat, but often you'll just see that triangle is delta, and that means that we've added some heat. Very often when you see that triangle, it means elimination, or some elimination is going to happen. Okay, there you have it. E2, E1. I will make one more video where we talk about how do we decide if we have an alkyl halide and something that can act as a base and a nucleophile. What's going to happen? SN1, SN2, E1, E2. Okay, stay tuned.